Welcome to the final part of this week's online lecture. In part 4, we will look at the effect of isotopic substitution and what happens when we relax the approximation of the rigid bond. So the question that arises when we consider isotopic substitutions is, does carbon-13 monoxide rotate the same as carbon-12 monoxide? Well, the one thing that I do know about these two different molecules is that the bond length is the same. I am sure you have seen a potential energy diagram for a diatomic. Well, you know that the equilibrium bond length can be identified when the potential energy is a minimum. So why would the minimum be the same for these two carbon monoxide molecules? Well, it is because the electronic potential energy surfaces of these two molecules are identical. This is because the electronic potential energy just depends on the interaction between electrons and electrons, electrons and nuclei, and nuclei and nuclei. It depends on the electrostatic interactions between those things. It doesn't depend on the mass of the nuclei. There is no gravitational term involved. It only depends on the electrostatics between the electrons and the nuclei. And the charges on the nuclei don't depend on which isotope you're working with. So the potential energy surfaces of both carbon monoxide molecules are identical. So there is no change in bond length upon isotopic substitution. At least no significant change that we need worry about. That means that if the bond length stays the same, then the reason why we see different rotational spectra is because the reduced mass is clearly different. The reduced mass won't be the same, and so the rotational constant will be different, and so the spacing between the lines will be different. So if this is the spectrum for my carbon-12 monoxide, my spectrum for carbon-13 monoxide will be different. In fact, the lines will be closer together. And the reason why is that the reduced mass for carbon-13 monoxide is larger. If the reduced mass goes up, the moment of inertia has increased. If the moment of inertia is increased, and because it is inversely proportional to the rotational constant, it means that the rotational constant decreases. If the rotational constant decreases, then the spacing between my lines decreases, because the spacing is equal to twice the rotational constant. And so the lines for carbon-13 monoxide are at a slightly lower frequency than they are for the corresponding lines in carbon-12 monoxide. For carbon-12 monoxide, the rotational constant is equal to 1.92 wave numbers, and for carbon-13 monoxide it is equal to 1.84 wave numbers. There are quite a number of interesting things that can be done with this. The intensities will depend on the number of molecules that are in that rotational state. Well, the number of molecules will be proportional to its abundance in nature. So if I look at the carbon-13 monoxide spectrum and compare it to the carbon-12 monoxide spectrum, the ratio of the intensities is proportional to their ratio of their abundances in nature. So I can use it to determine the natural abundances of isotopes. The other thing that I can do is accurately determine atomic weights. Because my moment of inertia is proportional to my reduced mass, and my reduced mass is inversely proportional to my rotational constant, the ratio of the rotational constant of carbon-12 to carbon-13 monoxides is equal to the ratio of my reduced masses of carbon-13 to carbon-12 monoxides. And if I measure these two rotational constants, I come up with 1.046. And I know that the atomic weight of carbon-12 is exactly 12 by definition. So therefore I can determine the atomic weight of carbon-13. And in fact this was done in 1950 when they used microwave studies to determine the atomic weight of carbon-13, and they found it to be 13.0007. This is a very good method to determine accurate weights of isotopes. Well, everything I've said so far has been about a molecule whose bond is rigid. What I want to do now is relax that condition. Well, why would I need to relax that condition? We know that bonds aren't rigid. We know that molecules vibrate, for instance. What is going to happen to a bond as it rotates faster and faster and faster? Intuitively, you know that the bond length is going to get longer and longer and longer. Why does the bond length get longer as we rotate faster and faster and faster? What forces are acting? Indeed, there will be a centrifugal distortion occurring. Now, I don't know whether in school you were told by your teacher that centrifugal distortion doesn't exist, that it is in fact centripetal force rather than a centrifugal force. Well, if this was the case, then your teacher was wrong. This cartoon relates it rather well. Let me act the role of protagonist in this cartoon and narrate it for you. How do you like my centrifuge, Mr. Bond? When I throw this lever, you will feel centrifugal force crush every bone in your body. You mean centripetal force. There is no such thing as centrifugal force. A laughable claim, Mr. Bond, perpetuated by overzealous teachers of science. Simply construct Newton's laws of motion in a rotating system, and you will see a centrifugal force term appear as plain as day. Come now, do you really expect me to do coordinate substitution in my head while strapped to a centrifuge? No, Mr. Bond, I expect you to die. How is centrifugal distortion going to affect my spectrum, though? Well, if we look at the CO data for this spectrum, here are the frequencies of each of these lines. In the final column, I have reported the frequency gap between adjacent lines. Notice that this gap is getting steadily smaller. And in fact, the size of these gaps is more rapidly decreasing as we get to higher and higher J values. So if I was measuring these lines at two significant figures, you wouldn't be able to appreciate that it is not always equidistant. There is only a slight variation. But this data is of high enough quality that we can measure that very slight subtlety incredibly accurately. This data is significant to the 6th decimal place. So we are very confident about this change. But it arises because the bond length is changing. You know that if I go to a higher J level and bond length changes, this will have an effect on the rotational constant. If the bond length is larger, the moment of inertia is larger, and so my rotational constant is smaller. So it is not surprising that the gap is getting smaller as I go to higher and higher J values. So delta nu, the change in frequency as I go to higher J values, decreases. And that is because the bond length depends on which rotational level you are in. Ultimately, this is because chemical bonds are elastic, they are not rigid. So if J equals 1, the bond length will be this length, and my molecule will rotate like so. If I go to J equals 2, the bond length will be larger, because it is rotating faster. The nuclei experiences centrifugal force, which stretches the bond. If J equals 3, the bond length is even longer, because it is rotating even faster. So the centrifugal force arising from distortion distorts the molecule, stretching the bond slightly. As the rate of rotation increases, the bond length increases, the moment of inertia increases, and so the rotational constant decreases. And it doesn't just have to be a diatomic, it could also be a polyatomic. Here I've drawn ammonia, and if you rotate ammonia around its threefold axis, these 3 hydrogen atoms will start to rise towards the horizontal plane the faster you rotate it. And in fact, this effect will be even more apparent than the stretching of the bond in the diatomic, because stretching a bond is a lot more difficult than what is happening here. We are not so much stretching the bond as bending the bond, and bending is a lot easier than stretching. Well, it's not exactly bending. The bond angle between the 3 atoms is changing as opposed to changing the bond length, and it is this motion that we refer to as bending motion. How are we going to improve our model then? We've got to take into account this effect, and we can do so relatively simply. And what we would do is to assume that my bond is allowed to stretch, but that it stretches in the same way as a spring stretches. If you have ever put masses on a spring and allowed it to stretch and measured the length, then you would probably have found that the spring obeys what is known as Hooke's law, that the force you will apply will stretch the bond proportional to the force applied, so that the displacement is proportional to the force. That leads to what is known as simple harmonic motion. So essentially, what we are going to assume is that my bond behaves as a simple harmonic oscillator. We'll be looking at that in more detail when we discuss vibrations. But we are going to assume the same model for rotation as we will do for vibration. So we are not going to have my rotational constant changing. We are going to keep the rotational constant that the molecule would have at equilibrium. And we're going to introduce another parameter, which we are going to call the centrifugal distortion constant, which we will give the symbol d. If we solve the Schrödinger equation, where we allow the bond to stretch according to the simple harmonic oscillator model, then this is the expression we come up with. The first term here is the term that we had originally for the rigid approximation, that is b times j into j plus 1. These set of parameters here are my rotational constant b. But I have a second term over here, which has a rather nasty set of parameters times j squared into j plus 1 all squared. This nasty set of parameters here is my centrifugal distortion constant d. So if I write this in terms of b and d, and in terms of wave numbers, then my energy is equal to b times j into j plus 1 minus d times j squared times j plus 1 all squared. My rotational constant is as before, but now notice that my centrifugal distortion constant d here depends on k. And I apologize for the confusion that arises here, because this k is not Boltzmann constant, it is a force constant. We use the same symbol, sadly. So this is the force constant, that is how stiff the bond is. If it is very stiff, I'd have a large force constant. The centrifugal distortion will be very small, so it won't affect the energy very much. The stiffer the bond, the closer it is to my rigid approximation. However, if my force constant is very small, for instance if it is a very weak bond, so rotating faster has a big effect on the bond length, then it is going to have a very large effect on my energy. It will change it substantially. If I know the force constant, and if I also know its reduced mass, I will be able to determine the frequency of the bond, at what frequency it would be vibrating at. Although I am doing rotational spectroscopy, knowing the force constant would enable me to derive the vibration frequency of the molecule. And that is what you can do here. Because the frequency of vibration is given by this expression according to the simple harmonic oscillator model. If I am able to determine d from my spectrum, I should be able to determine the force constant, and if I know the isotopic composition, I can calculate the reduced mass mu. This is the standard frequency expression for a simple harmonic oscillator. Now if you divide 4b cubed by d, you get the frequency squared. You can confirm this yourselves by using the expression for b and d on the previous slide. So if we are able to determine b and d, we can get the vibrational frequency, and we'll be returning to this when we discuss vibrational spectroscopy later in the course. The question I want to look at now is how the centrifugal distortion constant changes the appearance of my spectrum. This was the case for my rigid model, where my rotational energy term is b times j into j plus 1. I've got a new term now for my improved model, where I've got this additional parameter d, and it depends on my j like so. How does this change things? Well, when j is equal to 0, I haven't made any modifications, because d times 0 squared times 0 plus 1 all squared is still 0. In my new improved model, my ground state is still the same. But if j is equal to 1, my energy term is now 2b minus 4d. And if J is equal to 2, my energy term is no longer 6B, it is now 6B minus 36D. And the next one will be 12B minus 144D. Clearly, if D is very small, this won't be noticeable. But if D is large, or if the system is in a high J state, you will see the difference. And that's what we're seeing in the carbon monoxide spectrum as the gap between spectral lines got smaller and smaller. In terms of the spectrum, what will this effect look like? Well, this is my rigid rotor spectrum. And this is the spectrum I get for the non-rigid rotor. The lines are at a slightly lower frequency, and the gap is getting smaller and smaller as we go to higher and higher J values. Because I know the rotational term from my improved model, I can determine the energy differences in exactly the same way as we did before. I want to know the energy difference between level J plus 1 and level J. That will be f of J plus 1 minus f of J. So that will be 2B into J plus 1, which is what we had before, and an additional term, which is minus 4D into J plus 1 all cubed. I've got this new cubic term. And again, you can see why this reduced gap becomes more easily visible as you go to higher J values. It is because the spectral line spacing depends on J plus 1 cubed. So if J is very large, I'll be subtracting a very large value as we go to higher levels. In summary, centrifugal distortion leads to rotational energy levels that are closer together as J increases. Another way we can look at that, qualitatively at least, is that it is similar to the kind of behavior we had for a particle in the box. Remember that the energy of the particle in the box gets closer together as you increase the size of the box. Well, in essence, what is going on here is that as we go to higher J values, the bond length is getting larger. It is like the box getting bigger, and so the energy levels get closer together. For the same reason, the more space my molecule has, or the more space over which my wave function can spread, the smaller the gap will be between my energy levels. This improvement to the model, however, has not changed the selection rule or significantly changed the intensity pattern. The selection rule is still that it must have a permanent dipole moment, and the specific selection rule that delta J is equal to plus or minus 1 is still rigorous. The intensity pattern still depends on the Boltzmann distribution, just as it did for the rigid rotor. What are representative values for these parameters for a diatomic? My rotational constant is normally in the range of about 1 to 10. It might be slightly smaller than 1, that certainly can occur, but it is normally between 1 and 10. So then, of course, in terms of your spectrum, we're looking from, say, 0 wave numbers to 60 to 70 wave numbers if we're looking at a rotational spectrum. So remember, when we're only interested in vibrational spectra, we're working in thousands of wave numbers, and when we're working with electronic spectra, we're working with tens of thousands of wave numbers. So the spectral range we're interested in for rotational spectra are much, much lower. What about the centrifugal distortion constant? As I've said, it is very small, of the order of 10 to the minus 3 wave numbers. So it is 3 to 4 orders of magnitude smaller than the rotational constant B. This is why it is a small adjustment to my first model, and so why my first model was a very good model. So when we are working with small J values, it could be that we can ignore this term. The correction term D into J squared into J plus 1 all squared may well be negligible. This is the end of my online lecture for week 5. Thank you for listening.